So in the harmonic oscillator, whether it be a pendulum or mass on a spring, it's going back and forth. And so if you were to do something like exert a force on it, okay, so we're driving it. So we're exerting a force, and let's say it's a time varying force. Because if it's a constant force, then it's just all going to average out. But if it's time varying, so this is some kind of force as a function of time. If the force has the same period as the oscillation, that means you're always hitting it at the same time. So in other words, if this is going this way, you're hitting it every time, then the force is opposite the motion. So we know that work, which is the change in energy, is integral F dot dx. So if they're in opposite directions, that's negative energy, and so we're slowing down the oscillation. On the other hand, if we always hit it as it's oscillating in the same direction, then we're going to amplify it, because that means we do positive work, and we know that the energy of the oscillation equals 1/2 Ka squared. And so if you're hitting it, then you're adding energy to the oscillation. And so that's actually something that's kind of useful. It gives the idea of resonance. Now, one idea that had to do with that were water molecules. Water molecules tend to have a natural frequency of oscillations in the gigahertz. So if you hit the water molecules with a microwave that has a frequency gigahertz, then it tends to make the water molecules oscillate even more. That's the idea behind a microwave oven. So microwave oven, hitting a microwaves that oscillate close to the resonance of the water molecules, and so they absorb it, and so the additional energy, 1/2 Ka squared, they're absorbing the energy, and so you get a bigger oscillation. Same sort of thing with bridges. Okay, you have a bridge, and then as you go over the bridge, you push down on a little bit, there's a force back up, so because it's restoring force, there's going to be a natural oscillation right there, and so that natural oscillation would tend to make the bridge slightly oscillate. And so now you don't really want the bridge to oscillate, because then if you hit the bridge at a regular pattern, then if you accidentally hit that resonant frequency, the oscillate gets bigger and bigger and bigger, and well, bridges don't like to bend, so they eventually break and go collapsing. This is why soldiers route step across a bridge rather than marching in formation. Because back in the Middle Ages, they didn't understand how to construct bridges, and so it was possible to actually have a bridge that walking cadence could actually resonate. Now, there was a case a number of years ago in Oklahoma City that there was a hotel that had a suspended bridge, and they had a banquet going on, and they had music and people dancing here. And now it wasn't a rip-roaring dance, it was like a waltz, but the beat matched the oscillation frequency of this walkway, and it started oscillating and pulled itself loose from the ceiling and collapsed on the people below, and several people were killed. And so, again, this is an engineering issue. Our early days of aviation, there was a British aircraft manufacturer that made an aircraft, and the wings in an aircraft also, when you hit turbulence, they have to bend a little bit so they don't just snap off, and then they come back. And so one of these early jet aircraft, the engines were embedded in the wings, and so when you're taking off, you rev them up to high frequency, not a problem. When you were in cruising flight, you were at a frequency, no problem. But between these two frequencies would be what would happen if you're in a slow climb. Then it's possible that the frequency here was an even multiple of the oscillation frequency of the wings, and so the wings started oscillating bigger and bigger until they would snap off in flight, and that's generally bad for aircraft. And so, again, that's a resonance right there. You've occasionally seen a similar sort of thing here for example, cars. The springs or the suspension in the car is basically a spring, and once in a while on a rough road, you can hit resonance and cause the car to bounce bigger and bigger. Okay. And buildings, skyscrapers, the wind buffeting the skyscraper would tend to make the skyscraper oscillate back and forth a little bit, and you don't want it to keep oscillating until it falls down. And so what happens is high up in the building is actually a damper, something that absorbs some of this energy. So it tries to oscillate, and this thing absorbs the energy of the oscillation. And in modern skyscrapers, it's often a big mass that's held together with springs, suspended. And so it absorbs that oscillation. So instead of the building swinging, this thing starts swinging back and forth. Now, obviously, there's a limit. I mean, at some point, it swings to the point that it can no longer swing anymore. And so you can imagine, for example, a terrorist, instead of flying something into an airplane to knock it down, you have one guy standing down here at the bottom with a hammer, and they just tap it at exactly the oscillating frequency that the building wants to oscillate at. And what will happen is this damper will start oscillating bigger and bigger and bigger until it reaches its limit, and then the building starts oscillating back and forth until it collapses. Okay. Unfortunately, there are not a lot of terrorists that actually know physics, and so they don't actually know that this is something that's even possible. But this is the idea of a forced oscillation. And so with a forced oscillation, then what can happen is that you create this resonance. The resonance is the natural frequency that something wants to oscillate at, and if you have to add energy to it at that same frequency, then the oscillation gets bigger and bigger and bigger.